Welcome back to another lesson. Today we will continue our studies of finite difference methods. Specifically, our objective now is to link what we have already learned about Taylor polynomials and finite difference methods. These two concepts taken together unlock the door to even more powerful numerical methods. In the first line, I have written a Taylor series centered about x. It is truncated after the fourth term, as represented by an ellipsis. The second line is where I need to give an explanation. Notice that everything except the last term is identical to before. We still have h to the fourth, but I have combined 1 over 24 and the fourth derivative of f into a single constant. This constant is unknown, and for now, we don't really care too much about it. Basically, this constant is what helps us bound our error estimate. That is, we can use it to estimate how far our finite difference approximation deviates from the correct answer, which is often unknown as well. It may be confusing now, but just wait a few minutes until we plug some actual numbers in and look for patterns. The important takeaway for now is that the error is a function of h to the fourth in this particular case. That is why in the third line I have simply written it as O h to the fourth. You may see this labeled as big O notation, and I encourage you to do some more research about it if you are curious. Consider the forward difference we derived in a previous lesson. Now we will derive it from the Taylor series. In this case, I have truncated the series after the first derivative. The resulting error term is of order h squared. In the second line, I rearranged the terms to isolate f prime on the right-hand side. In the third line, I have rewritten big O notation as a constant multiplied by h squared. Since we don't know if the constant is positive or negative, I have chosen to add it instead of subtracting. This is fairly common practice in numerical analysis. In the fourth line, I divide each term by h. Notice that h squared divided by h leaves me with h. Thus, my error term has been reduced to order h. That is reflected in the fifth line, where I have also moved f prime to the left-hand side. The sixth line is using subscript notation. It is equivalent to the fifth line. I just wanted to expose you to some notation you might see elsewhere. Here is a picture showing notation with x plus h and f of x plus h. That is equivalent to I plus 1 and f sub I plus 1, as can be seen in this picture here. We can run through a very similar process for the backward difference, as can be seen in this screen. The end result is in fact the same formula I used in the previous lesson when I first introduced backward differences. Now let's talk about that error term. These numbers are pulled directly from the previous lesson in which we used finite difference methods to approximate the derivative of y equals sine x at x equals 0.8. Look at the absolute error row for both h equals 0.2 and h equals 0.1. By cutting our spacing in half, we more or less cut the error in half for both forward and backward differences. So what's going on with the central difference? First of all, notice that the error is much smaller than for either forward or backward difference. Secondly, when we cut the spacing h in half, we reduce the error term by a factor of 4. This is because the central difference is of order h squared, as opposed to h. In general, the higher order our method is, the smaller our error will be. For example, a method of order h cubed would be even closer to the true value than anything seen here. What if we subtract one Taylor series from another? Well, this is what I have set up to do here. I've truncated each series after the second derivative, so both are of order h cubed right now. Also notice that expanding f of x minus h changes the positive sign to a negative one after every other term. Otherwise, it is identical to f of x plus h. For clarity, I've distributed the negative sign to each term in the second row. Adding a negative is equivalent to subtracting, and this can be done term by term. The result can be seen here. Notice that f of x canceled out, along with the term for f double prime. In the first line of this page, I've simply rearranged the order of terms. In the second line, I've divided each term by 2h. Notice this has reduced us from a third order error term to a second order. In the third line, I've simply restated the result using subscript notation, which we already discussed. The final result is what we used to compute a central difference approximation in the previous lesson. in which finite difference methods were first introduced. One note on big O notation. You may have noticed that when we divided each term by 2h, that didn't produce 1/2 OH squared. This is because 1/2 is a constant. All we care about for big O notation is the order of h. Taking a look at this table again, we notice the same thing as before. The error term for central difference is much smaller than that for either forward or backward difference. This is because it is of order h squared, whereas the other two are of order h. So now we have seen a connection between Taylor series and finite difference methods. Stick around for the next part of this lesson. We will explore this connection even further.